Hi everyone, the main topic of this video is about flywheels. Alright, before we start, I prefer you pause the video and think about the question first. Okay, in this problem, we are required to find the maximum fluctuation of energy, which can be obtained from this relation. Delta E equals to the mass moment of inertia I, multiplied by the average rotational speed omega squared, multiplied by coefficient of fluctuation k. By now, we know what parameters we need to calculate, so we calculate the I from the givens of the problem, which equals this value you see on the screen. Next, we calculate the average rotational speed, and then we converted this value into rad per second by multiplying it by 2 pi over 60. And finally, we calculate the k from this relation. Now we calculated all the parameters we need, so we get our answer for the maximum fluctuation of energy. Now for question 2, again I prefer you pause the video and read the question first. Okay, let's do some brainstorming. We are required to design a suitable flywheel, and in order to do this, we need to get the mass moment of inertia I, and the only way to get this is through the maximum fluctuation of energy, so we need to get this term first. Alright, so there's a statement that the coefficient of fluctuation of energy is about 40%. Now, this means that delta E over the work done per cycle is equal to 0.4. So rearranging the terms, the delta E is 0.4 the work done per cycle, and now we need to get the work done per cycle. Now the work done per cycle is the average torque multiplied by theta per cycle, the crank angle per cycle, and the average torque is calculated by this relation, the power over the average omega, and we already have these two values as given in the problem, so we can get the average torque. And for the two-stroke engine, the theta per cycle equals to I, so now we can calculate the E per cycle, the work done per cycle, and therefore we can calculate delta E, the maximum fluctuation of energy. Now don't forget, we are trying to get I, and the only thing that we don't have yet is the K. And there is a statement in the problem that can help us to get that parameter K. It says that the speed variation should not exceed positive or negative 1% of the average speed. This means that the maximum omega should be within 1.01 the average omega, and the minimum should be 0.99 from the average omega. And therefore we can get K from this relation, and it would be 0.02. Now we can get finally I, the mass moment of inertia, and it equals this quantity. As we already have I by now, we can assume the mass and the geometry of the flywheel while considering the geometrical constraint of the engine. The problem stated that the maximum dimensions of the engine shouldn't exceed 3 meters, then the diameter of the flywheel shouldn't exceed the 3 meters, and the radius of gyration should be well below 1.5 meters. So you can just say the radius of gyration should be exactly 1.5 meters or less than 1.5 meters. It has to be well below 1.5 meters. Now to clarify this issue, we will have like quick overview about radius of gyration, just to make sure we are on the same page, you understand what does it mean, what's the meaning of the radius of gyration. Now if I have, for example, a solid disk, then its mass moment of inertia around its center is given by I equal half mr squared, where r is the radius of the disk. If we, for many reasons, are interested to represent the disk as a particle that had the same mass, then it should be placed at a distance from the center that we call this distance the radius of gyration. And since both i's here from both models are the same, you may equate both equations together and end up with this relation that the r, the radius of gyration from the lump mass model, would be around or approximately 0.707 from the radius of the disk. So you can see that the radius of gyration would be less than the radius of the disk. This is just a quick example to show you the difference between the radius of gyration and the actual radius of your geometry. So as a recap, you have to make sure that the radius of gyration is well below 1.5 meters for the reason that we already stated here. Let's move to the final question in this tutorial, and I think you know what to do here, right? Okay, let's do a quick brainstorming. First, you have to find the mass of the flywheel, and the only way to do this is by calculating the mass moment of inertia, and we get the mass moment of inertia from delta E, the maximum fluctuation of energy. In question number 2, we got it from the coefficient of fluctuation of energy, but in this question we will get it from the turning moment diagram. So the work done per cycle equals the average torque multiplied by the crank angle per cycle. The average torque is given by the power divided by the omega average, and both of these quantities are given in the problem. Because this is a 4-stroke engine, the crank angle per cycle equals to 4 pi. Now we can get the work done per cycle, which equals to this value. This is the turning moment diagram, and we ignored both of the suction and the exhaust strokes. We can write the work done per cycle as the work gained from the expansion stroke minus the work done to compress the gas. And from the problem, we know that the work done to compress the gas is about 25% of the work gained from the expansion stroke. So rewriting this equation, we end up with the work done per cycle equals to 0.75 the work gained from the expansion. And accordingly, we can calculate the work gained from the expansion to be equal to this value. Now from the turning moment diagram, we can make use of this value. The work gained from the expansion equals to the area of the triangle CFH, and the area of the triangle CFH equals to the half base times height. Here the base CH has a value of pi, and the height of m is the value of Tmax, it's a maximum torque. From this equation, we can get the maximum torque. Now, the area above the average torque is the maximum fluctuation of energy, and it's denoted by the yellow triangle EFG. Using similarity of triangles EFG and CFH, we can construct this relation, and from there we can calculate the EG. Now we can calculate the area of the triangle EFG, which is half times the base times height, and after we obtained delta E, the maximum fluctuation of energy, we can calculate the I, mass moment of inertia, from it. And once we obtain the I, we can get the mass of the flywheel. Alright, this concludes our tutorial. Until next time, thanks for watching.